Hi, I watched a few videos of AI playing Snake and got curious about its strategies when multiple snakes are involved. Let's explore this further. I have programmed a basic snake game in which the snake's movements are controlled by a small neural network. It appears to be functioning quite well. Let's quickly explain how it works. The snake sees in 8 directions, which provide input for the neural network. A positive number represents food, while a negative number indicates an obstacle. Based on their values, the input neurons send the values multiplied by the weights of the connections to 4 output neurons. The highest number in the output neurons determines the direction the snakes will take in the next move. The networks are randomly generated and not very proficient at playing Snake. To improve their performance, I programmed a simple evolutionary algorithm for training them. The networks can undergo modifications or mutations, if you will, such as adding or removing connections between nodes or changing connection weight. Another type of mutation involves splitting a connection and adding a node. We will call a group of networks with the same node configuration a species. Initially, the randomly generated networks play a few games of Snake. The weakest ones are eliminated and replaced with copies of the best performing networks. These copies are then subjected to a slight mutations. With each subsequent generation of networks, the average score they achieve should increase. That's all for the explanations. Let's place 10 snakes on the board and observe how they manage to coexist. After 10 generations of evolution, they remain quite oblivious. To discourage them from colliding with the wall, I added a scoring penalty for dying, which gave an advantage to snakes that avoided walls. After 50 generations, they finally learned to minimize collisions with the wall. After 300 generations, they grew quite long, but often perished due to collisions with their own bodies. Therefore, I removed the restriction that prevented snakes from moving over themselves. This helps, but a new problem arises. The snakes will stay in one place if they decide there is no better place to move, although there usually is a better place to move. It is safer to stay in one place, not risking running into walls or encountering other snakes that appear randomly. A snake can maximize its score by searching for food only when its surroundings are relatively safe. So I added a new rule. Snake will lose a one body segment after 15 moves. A snake with a 0 body segments is obviously dead. This rule is intended to encourage them to find food instead of staying in one place. Now, snakes will search for food, but when there is an obstacle, they will try to avoid it. By doing this, they divide the grid into little sectors, like territories, that they occupy to hunt for food. When a snake dies, its territory will be slowly taken over by surrounding snakes. If we remove the walls, we can observe this behavior even more clearly. I was hoping to discover some interesting behavior thanks to interaction with the other snakes, such as cornering them and forcing them to crash into a wall. To encourage this type of interaction, I introduce an additional rule. When a snake dies, it leaves behind one piece of food for each body part it had. Once again, things don't go as intended. The dominant strategy seems to be running into the wall as quickly as possible, respawning, eating the corpse, and repeating the process. I initially thought that a better strategy would evolve after a few generations, such as consuming the corpses of other snakes and avoiding walls. However, it turns out that due to the rules I introduced, this is not the optimal strategy. There is a maximal number of food that can be on the grid. When the limit is reached, no new food will be added, and snakes have to eat what is available on the grid until the number of food items is reduced below the limit. However, when a snake dies, it respawns with 3 body parts. If it dies immediately after respawning, One food is added for each of its body parts, even if it exceeds the limit. This way, the grid will get filled with food pretty quickly. Snake can just run from respawn to the wall, eating everything on the way, crashing, and still achieving a high score, which allows him to advance to the next generation. By imposing a significant penalty for dying, we can observe behavior similar to blocking other snakes and forcing them to crash. The snakes now move from side to side, creating enclosed spaces. When other snakes spawn in such a space, they usually crash and are consumed by the enclosing snake. Because the neural network and training algorithm are so simple, this is the best behavior, resembling snakes trying to eliminate other snakes, that I've achieved. When a snake dies, it receives a score penalty and respawns. How would the evolution of snake behavior look like if, after dying, snakes wouldn't respawn and the only way to create more snakes would be by making more copies of existing ones, like reproduction? Let's try a new rule. When a snake reaches a length of 6, it will split into two snakes of length 3, and the child snake will get a copy of the parent's neural network with a small mutation. At the start, snakes spawn and most of them disappear after several moves without eating food, but some of them manage to grow and produce offspring. At one point, a relatively successful species emerges. It is capable of eating more food than it needs for movement and starts spawning child snakes, whose numbers grow quickly, until the screen is full of them. Let's make another adjustment. Now the snake has a fifth output neuron that determines when it spawns a child snake by splitting in half. Some snakes will reproduce as soon as possible, while others reproduce rarely or not at all. Unsurprisingly, those reproducing quickly will fill the grid. Because they frequently reproduce, these snakes remain short. However, as their population increases, they consume more food than can be replenished, leading to a subsequent decline in their numbers. Over time, the species capable of more efficient food foraging will thrive, resulting in longer snakes than those present at the beginning of their evolution. Evolution tends to favor species with the longer snakes because when a snake divides in two, each must find food for its movement, requiring twice as much food to survive. Snakes become longer, but not excessively so. Species that do not reproduce through division will sooner or later crash and die without offspring. The length of snakes will therefore reach a balance determined by the availability of food. I have some other ideas for adjusting the rules to simulate evolution in computer model, but this project was not designed for such a purposes, so I will show you in another video. See you there!